Welcome to this webinar. We'll be presenting solutions that target issues related to process manufacturing using deep reinforcement learning. I'm going to say that a lot. I'm probably going to mumble a few times, so bear with me, please. We will use the Microsoft Project Bonsai deep reinforcement learning toolchain to illustrate this approach. After a quick introduction of Neil, we'll go through typical manufacturing challenges that autonomous system can help improve. I'll start at a high level explaining what autonomous systems are and what are the key components that make an autonomous systems. And then we'll double click a little bit into the Microsoft Project Bonsai toolchain. That is a toolchain for deep reinforcement learning from Microsoft. I'll then go through a quick demo of Bonsai for you to see how you could yourself play with it. And then we'll spend the remainder of the presentation in an actual case study of a customer of ours, PepsiCo, that used the Microsoft Project Bonsai platform to deploy AI on their manufacturing process. So let's get started. First, a few words about Neil. As Jim mentioned, Neil Analytics is a recognized cloud engineering and AI Microsoft Gold partner. We offer end-to-end business transformation consulting services from the strategy aspects to the execution, cloud data or AI implementation, to the operationalization and activation. That is, ensuring that those AI and ML models get integrated into existing processes and apps. We can engage very flexibly by augmenting your existing teams, handling projects end-to-end, or even outsource completely services and manage them for you. If you have any questions about Neil, I'm happy to answer them during the Q&A session or afterwards. So let's dig into the core topic for today, deep reinforcement learning and the Microsoft Project Bonsai for process manufacturing. Let's get first into the process manufacturing challenges. Throughout the years, Microsoft has developed solutions for AI, and Neil have been developing AI and ML solutions for process manufacturers. To level set the discussion, let's start with a common model about typical elements in process manufacturing lines. Typically, one or more raw materials are fed into some equipment to get mixed, extruded, melted, frozen, or any other chemical or mechanical process. Often, this step is followed by one or more additional steps. There will be further processing the first step outcome by baking it, cutting it, freezing it, whatever is necessary. You could imagine also those same process with chemical vats, paper pulp digesters, and so on, whatever is applicable in your case, or in the case of plastic, additional plastic manufacturing steps. One of the first process challenge out of the top 5 that we've identified is start time. The longer it takes to start a process and to achieve nominal value, the more it will cost the company. A second typical issue is specification drift. This happens when the product is not really out of specification, but starting to drift from its core target value. Let's say you want a piece of plastic rod to be 2 inches, and you start and plus or minus a quarter inch, and then you see that it's starting to be an eighth of an inch too long. Well, you want to be able to catch that before it becomes out of spec. And if that happens, you want to be sure that you can control the end product quality and reduce waste as much as possible. Whenever you need to shut down the line because there is an issue or you need to change product, you want to be sure that you reduce this shutdown time. And finally, when everything is running just fine, you probably want to try to minimize the energy consumption. When you look at all those 5 typical challenges, they're not the only one, but they are typical ones. There are lots of elements, parameters that can impact them. Raw material viability is a clear one. But equipment state, wear and tear, it could be, for instance, the difference in behavior in a piece of equipment between 2 parallel production lines. The operator expectations. We all know that experienced operators will be able to see things before they happen, to fine-tune things by having access to those heuristics they have built by working 5, 10, 15 years on this line. The operating environment. Think about temperature in a manufacturing plant, the humidity, or any other parameters can have an impact as well on any of those challenges. And the last example, but those are not the only 5 ones, is the skew type. If you do a 5 inches rod versus 2 inches rod, maybe the system is different. If you do different types of plastic, you use different type of plastic as an input, maybe it's going to be different. There are many more like those, but let's start with those 5. So how could you try to reduce those challenges? Well, typical command and control systems have their own limitations. Traditional control and command systems are focusing on set points. They're based on static, predefined goals. They can't really adapt to changing conditions, and they usually leverage very simple sensors. Theoretically, AI could do much better. However, there are other challenges associated with using AI in real-life manufacturing solutions. First, there is a lack of labeled data that can be used for training. Then, if we can't test an AI on a live system, if something goes wrong, you can easily imagine the damage it can produce and the dangerosity of that aspect. Finally, your experts are process manufacturing engineers, product engineers. They're not AI engineers. So there is a lack of data science expertise at the company level that doesn't really allow you to quickly build and efficiently build and train AI agents. So in the remainder of this presentation, I'll share with you a relatively new type of AI solution called autonomous systems. An autonomous system can help solve those AI challenges and help improve those 5 manufacturing processes challenges, as well as others. So let's dig now into the concept of autonomous systems themselves. There's 3 key elements in autonomous systems: machine teaching, deep reinforcement learning, and simulations. But first, where are they applicable? Autonomous systems are best used when they need to control complex and dynamic processes, or processes that need to adapt under changing conditions. For instance, raw material variability that we spoke about in the previous slide. Operator experience that is changing from newbies to the old guards. What they will do is they will help you add this additional layer to create a closed loop system, a true end-to-end view and control system for your manufacturing, beyond the control at the equipment level. At that stage, you may be wondering, what are the difference between autonomous system and automated system? So here's kind of a simple way of thinking about it. Automated system, that's the traditional automated system using PLCs and PIDs and those kind of controllers. Simple and defined automation. You could have, for instance, a PID controller controlling the flow output of a pump. But what happens if the fluid in the pump has different viscosity depending on external factors? What happens if the pump starts to wear out and its yield changes? In those kind of situations, traditional automation systems will require lots of human supervision, adaptation, or might even not be able to appropriately drive the process appropriately. If I come back to my example of the pump, and the fluid is, for instance, an oil that increases a lot in viscosity when the temperature drops, the pump might not be able to reach the desired output pressure when the outside temperature drops. You could imagine the same concept with different types of plastic inputs, for instance. This is where autonomous system can really shine. Autonomous system can optimize operations by sensing and dynamically respond to a changing physical environment, for instance. In a pump example, for instance, an autonomous system could dynamically change the pump controller set points to ensure that regardless of the outside temperature, the output pressure of the fluid remains at the optimal level. So how do autonomous systems work? First, they're AI-powered agents, but they're built using human expertise. Could be one or more, depending on your system. And as you've probably already guessed, they're using the latest deep neural network technologies. They're not based on statistical machine learning. They're using neural network technologies. The way to design it is, first, we are going to use a concept called machine teaching. Machine teaching is not a technology. It's a thought process. It's a development process where working with your operators and R&D teams' expertise, we'll try to define what are the most relevant system variables, what are the most important parameters to look at to optimize the system. For instance, temperature might be very important, but pressure and humidity, not so much. If there are competing goals when it comes to optimizing the system, let's say energy use and being close to the specification you have defined, we'll use that as another input to tune this AI agent, this deep reinforcement learning system. The way we will train it is using what's called deep reinforcement learning, and I'll come back to that in a second. And to do that, we'll have to use simulations. Once the system is trained, we will then deploy it. So if you think about the traditional process controller, the AI agent will sit on top of and talk directly to the process controller. We call that a brain in the Microsoft Project Bonsai vernacular. This AI agent will close the loop by directly controlling the controller or controllers of your automated production line. The closed loop manufacturing continually feed information about how product perform, say their size, for instance, and they allow the process to be quickly adapted before scrap or rework get out of hand. While closed loop manufacturing has always been a goal for manufacturers, analyzing the data in real time was really, so far, not really possible. Now, with smart and connected IoT sensors and actuators, AI agents, closed loop manufacturing can include real-time information and smart information, advanced information, not only simply connected to the set points of a particular controllers, for instance, and data from product while in production. In a full closed-loop automated system, the AI agent will directly monitor and control the system. Another option could be, if you have a SCADA HMI, to, through the SCADA control audio controllers, or simply display on the HMI advice that then the operator can decide to choose or not. Take a bit the analogy of a doctor that will use AI to get a diagnostic. The AI could go and deliver the medicine, or the AI could say, hey, I believe it's this kind of disease, and I believe that this kind of medicine that you need to give. You're the doctor, you decide. And very often you'll see customers will start with this operator-driven closed loop. It's almost a closed loop, but not really. And then as the performance of the system increase, then the system will slowly take over to allow more scale throughout your production lines, across operators, and potentially across factories. As you may have guessed already, one of the issues here is going to be, how do we get the right data? One of the key elements here is to be how can we measure and capture the right data to close this loop. And that's where smart IoT sensors can make the difference. I will now leave the floor to Mohammed from Microsoft, He is an IoT expert, and we'll give you a bit more information about what are the options and the journey. Mohammed, the floor is yours.
Thank you, Olivier. When we think about smart IoT sensors, we need to think about a journey from crawl to walk to run. The higher we get, the higher the intelligence of the sensors, and therefore the larger the need for advanced connectivity, processing, management, and so on. The first step is just to use the existing sensors and actuators connected to the controllers. In that situation, you will be able to develop an autonomous systems if the data captured by those sensors is sufficient to gauge and monitor what you wish to control for. However, very often, as you get into a closed loop approach, existing sensors won't be enough, at least not on their own. The first step is to therefore to extend the sensor's capability by bringing the intelligence at the edge that they will connect to the existing sensors and add local processing or and other storage technologies capabilities. And like in Azure, we have the AI capability at the edge, we have streaming analytics, we have Azure logic apps, Azure functions. You can take advantage of those for doing all the pre-processing at the edge level. And then the final step is to deploy natively smart sensors that will run local AI or machine learning models or perform advanced computing tasks at the edge. For instance, you could deploy a vision AI model on an Azure Stack Edge to monitor in real time the physical characteristics of a product. For instance, its length, width, color, you name it, or any kind of damage or any kind of changes. Oliver, thank you. Back to you.
Thank you, Mohammed. So let's go back to the process of building and deploying autonomous systems. There are five big steps, and I'm going to go through them at a fairly high level, but enough for you to understand what those entail. The first one is machine teaching. Machine teaching, as I mentioned, is more a process than an actual technology. If you think about deep neural networks, one of the most challenging issues is that it is impossible for a human to really know what's happening inside the black box that the multi-layer network is. For instance, you can't always be sure whether a particular input is actually relevant, and if it is, how much so. As far as the deep nodes are concerned, it's virtually impossible to know which node impacts which outcome and how it does it. So machine teaching will help you parse out this information by leveraging human expertise to inform your solution design. You're going to raise what's called explainability of the neural network by ensuring you capture the right sensors, the right actuators, use the right decision criteria to train the model based on inputs and outputs that your experts have defined. Typically, they will select, sorry, they will select the process engineers, the operators, the R&D experts. Those practitioners will be able to help the AI developers select the most relevant process inputs. They'll define one sensor, data will be the most important, and maybe other factors, let's say humidity or temperature or noise or any tribal knowledge that is not necessarily documented can then be leveraged by the AI system to increase explainability and performance. Another type of input selection will be the product attributes. What are the appropriate product specification coming out, the size, color, shape, any other parameter. One of the, on the output selection aspect, by the way, manufacturing expert will help AI developer choose the controller parameters that should be selected. Maybe a particular parameter that, let's say, speed of a screw in an extruder. Maybe it doesn't really impact the broader system, and it's controlled really well by the PLC based on whatever parameter that you control. So you don't want to touch that. But the set point of speed of the cutter, That may be something important. All those kind of things are not things that the AI expert will know, but your operators, your process engineers will know. And together, the team will define those parameters. That's a big part of the machine teaching. Another one, and bear with me, this is just a conceptual view, will be to define the scope of applicability of your AI, of your AI agent, what I call the operational universe. One way to think about the application scope is something that refers to the range, input, and output um, for all the variables of your system. So in a very simple system, you could say my system needs to work between those and those temperature, A and B, and those pressure points. Obviously, the vast majority of systems that you want to control won't have only two variables to take care of. In this other very simplified example, we'll have three variables. So it's a three-dimensional operational universe. So once again, this is a very simple example because it's only three variables and a very linear model where everything is nice and square. Obviously, real life is not like this. So it's just take that as a visual illustration of the concept, not actual real life things. Because in real life, there also could be different ranges based on different factors. Like, for instance, different sets of temperatures could have different types of pressure and speed requirements. Once again, those forms are just easy to pick in PowerPoint. They're not real ones, but that gives you an idea. How do we define this operational universe? Well, the AI cannot learn that. That's what we get through the machine teaching process by extracting the knowledge, the experience, and any heuristics that your teams have developed throughout the ages. A second key element in AI agents for deep reinforcement learning is the concept itself of deep reinforcement learning. So what it is? It's a concept where the AI agent will train by itself. Through trial and error, it will converge to the optimum point. And because obviously it cannot use a real-life system to achieve that, it will have to leverage process simulations. So before I drill a bit more, I really want to highlight the difference between deep reinforcement learning and traditional AI. Technically, deep reinforcement learning is not new. The very first deep reinforcement learning tests were in academics in the early 90s, but really it became a viable option only for the last few years. So typically, when you do a traditional AI training, you will have your inputs, whether it's text, image, videos, sensor data, you name it. And then you'll say, okay, for this input, here is a human will have tagged that. Here is what the output that I expect. Let's say real life examples of that. Let's say, for instance, you want a speech recognition system. You will associate the sound, the acoustic aspect of the sound, the wave, to the phonemes. I like bananas. If it's a picture, you'll add the tag banana to the picture. If it's a translation, you'll tag mi piace le banane in Italian to I like bananas in English, and so on and so forth. Once you have those tag data, the system will run through the AI, and based on the difference between the actual output of the AI and what the expected output, this will be used using the gradient method to tune the AI system. Obviously, in your manufacturing plants, you don't have this data. You don't have millions of data points at the ready, human tagged for you to train an AI. Deep reinforcement learning works because the AI agent will use a process simulator to train itself. The AI agent will send an action to a simulation that will reply with a state. Then a reward function that has been defined with your process experts will, as the name says, either reward or punish the AI agent for a good behavior or bad behavior. Think of it like teaching a dog to sit. A bit more complex, but that's the concept. So as you go through tens, hundreds of thousands, often millions of cycles, the system will slowly converge to a performing AI agent that can then be deployed. As you can see, we talked about machine teaching, we talked about the concept of training, but there is a key element, which is the simulation design. Simulations are critical in deep reinforcement learning. No simulation, no deep reinforcement learning. Something important to keep in mind is that this is not a small step. Unless you already have a model available, this can take several months. And there are lots of benefits doing simulations because you're going to learn more about your process, you're going to put on paper tribal knowledge, and you'll have a model that you can use for what-if analysis, for instance, or to create a digital twin by connecting it to your actual system. There are several ways of building simulations, and the three critical ones, the one you see the most often, are physics-based, where you'll use the law of physics, and you'll see an example very soon, to simulate your system. It can be very complex. It requires lots of skills that not necessarily in-house. I mean, you have to be a plastic extruder designer and physics expert, physics of fluids expert, to build a simulator for an extruder. Another option is to use software packages, where companies like AnyLogic, Simulink, and others will offer blocks that you can combine. They're very flexible. They have a very, very large library of single components. They're not applicable for everything, but they're quite a quick way to get something together. OpEx-wise, it's an ongoing cost, obviously, so that's something you keep in mind, but they're very popular. The third one is AI-based, where instead of trying to model every single element of your process, whether it's one piece of equipment or several. Well, I'm sorry, just realized I'm all blurred. Oh, here it is. I'm moving too much. Sorry for that. Instead of modeling only one piece of equipment, we will look at your whole manufacturing chain, whether it's one or two pieces of equipment, as one black box. And the AI will train to just mimic the behavior of the system. It doesn't really know how it's done. It just knows that with those inputs, we get those kind of outputs. But it demands lots of data, training data, and expertise in the AI space. So you have your simulator, but you have to be very careful about the limits. First is never perfect. So you need to know the limits of the simulator. You also have to understand that there is equipment wear and tear. And a simulator for line A might not be appropriate for line B, despite the fact that theoretically it's exactly the same piece of equipment. And you also have to have clarity about the input range. If you train your simulator using temperature between 190 degrees and 240 degrees, you need to know that. And you need to be conscious about that, because the data system is above 240. You'll have to turn off your AI because it hasn't been trained beyond those limits. So we talked about all the different elements. Let's talk a bit now about the Microsoft Project Bonsai platform itself. Microsoft Project Bonsai platform, as we discussed, will help you have one toolchain to manage the 5 different steps of developing an autonomous system AI agent. It's an integrated toolchain, and they will support your project from inset, from the machine teaching, all the way to deployment. First, you'll be able to integrate in your solution either one of the simulators that are given as in the platform as samples more than anything else, open source in most cases, or you'll be able to integrate third-party simulators, whether they're physics-based, let's say a Python model, whether they're using an AnyLogic or Simulink model, or whether it's an AI-based model. Then you'll define a training curriculum, and the system will be able to train using reinforcement learning and the simulator your model. Once the model is trained, you can test it with the simulator, once again, in the platform. And when you're happy with the result, then you can export the brain, the AI agent, to the cloud, to the edge, or if you prefer, on-premise. What's super interesting for you as a manufacturer is that your process engineers will be able to participate in this AI creation without being or becoming AI experts. They will teach AI um, with instructions that are linked with their experience of the process, their heuristics, their knowledge of a particular machine. And that's why operators as well are part of this process. So let's go to a short demo. Just as a quick word of warning, it's very quick. I didn't want to bore you with the 5 minute things. The more extended demo is available online. And of course, it's a self-demo. You can do it yourself on Project Bonsai. But that'll give you a bit of an idea of how does that work when I want to build a model in Bonsai. If you think about the model, it's a model for, it's an example for a plastic extruder. So the first thing we did, Neil Analytics developed the extruder demo that is inbox in Project Bonsai. And as I said, the source code is all available on Microsoft GitHub repository. Our expert went into the physics. So we talked about physics models, remember, that's an example, to the physics of melted plastic, screws, dies, all those kind of things, looking at the properties of the screw, speed, physical form, and so forth. The PVC, that was the plastic we selected, the viscosity of the PVC, its actual temperature inside. So for instance, we made a quick assumption. We said, okay, the temperature of the PVC is given and is the same throughout the screw. We all know it's not true. In real life, the temperature will slowly raise as it goes through the screw. But we needed to do some kind of simplification to make a model that is workable. The die is very simple. It's just little plastic rods, spaghettis of plastics, if you wish. Very simple. If you were to change that to, say, U-shapes, for instance, you'll have to redesign part of the model. And already with that, it's a fairly complex model. Sorry for that. So if you go to preview.bonsai.ai, you can scroll through the different types of demos. You select extruder, give it a name to the project, and that will create a default brain. And you will have what's called the inkling code, which is a training code. You can see two training concepts, one where you control for the length, the other one for the yield. You want to be sure to use as little plastic as possible. In the code of the inkling, you'll be able to see the core variables that are sent to the simulator, which is a separate Python program, and then the curriculum that defines the training itself. You can see that you can define, for instance, what the acceptable PVC rod length, your target, how many episodes, which is the number of trainings you want to have. You also have a visual view of doing that, so you can drag and drop elements if you already have them or you import them for something else. And then you start training. So you first train the first concept, you click on it, and you'll have to connect it to the simulator. And if I go into the visual editor, you can see that this is connected, and you have this whole loop where the brain will send something to the simulator, and that will come back. You can start the training. That's why I recorded it, because it takes about 30 minutes for this example. You can see, if you look in the bottom, you can see that there are several simulators running in parallel. 20 simulators here. There could be hundreds. You can decide. So you can use the scale of Azure to go as fast as necessary. As training advances, the AI agent converges. You can see the nice little curve flattening, because now 100% of the time you get the right rod length. And when it's done, you can then switch to the second model. 20 minutes later, you're done. So it will then build the selector, which is this little box that will select one or the other, depending on what you want to do. And when you finish, you can export the brain into a container. You can decide which distribution, which 32 or 64-bit. And once you get that Docker deployment, you can deploy it on an Azure IoT, for instance, device, or a PC that you have locally, an Azure package, whatever is necessary, or whatever you decide to do. As I say, it was very short. You can spend more time on the demo. You can find it on YouTube on Neil Analytics channel, and obviously it's in box with Project Bonsai. And it's all free. You can go and play by yourself. Everything is in box. So we talked about manufacturing challenges, autonomous systems and DRL and all those kind of things, deep reinforcement learning. That's all theoretical. Now let me share with you an example of an actual project. It's not plastic, it's food extrusion, but conceptually it's very similar. This is a project that Neil worked on with Microsoft for the Microsoft Pepsi team, and with the Pepsi team, because as I mentioned several times, this is not something you just outsource. This is a close collaboration between whoever is developing the project and your process engineers, your operators, and so forth. Sorry about that. So deploying Project Bonsai at Pepsi. When you and everything confidential have been obfuscated, obviously, but at a high level, creating a Cheetos, those deliciously addictive snacks, has several steps. You extrude the cornmeal, bake it, and when it's formed, add the seasoning and package it. Specifically, Pepsi wanted to optimize the extrusion and baking process as one element. So, as we discussed, the first step is machine teaching. By using machine teaching, they were able to select 7 key variables, including the snack visual appearance, as the one that had to be measured to ensure, like, input to the AI agent to ensure that everything is correct, or that could be controlled, sent back to the PLC to adapt the manufacturing in order to get the right results. Great, but how do we simulate that? As you may have guessed, that's kind of hard to do when you talk about visual appearance and things like that with physics, for instance. So what they did, they built a product characteristic measurement system, a vision system at the edge. And then they just plugged everything into the existing Cheetos line and monitor both the controller state, those rates and speed and everything, and the physical by measuring automatically the length and the curvature and so on of the Cheetos. And that created millions of data points that could be then being used to create an AI simulator. It's not deep reinforcement learning, it's a traditional label data AI model. But now you have an AI model that mimics the behavior for the key variables, inputs and outputs of your extrusion process, or in that case, extrusion plus baking process. The AI has no idea how everything works, has no idea about, no concept of rotation of a screw, or die size, or even the temperature, like the control of the temperature of the oven. It just knows there is a certain temperature. Then, when the simulator was built, we could train the model. So back to our concept of deep reinforcement learning. The Bonsai brain will send those 4 variables to the simulator. It will come back with the same 4 variables and actual values and the visual appearance, pressure, and temperature, and run that hundreds of thousands, if not millions of times, until it converged to a system that could control this AI simulator. When that was done, we could then go to the deployment aspect, where the brain was then deployed and it's talking to the extruder controller to get and send the data. But it's also getting the data from the system. Although technically, that will be the end result. A first step is always to use a human in between. So instead of sending the information directly to the extruder controller, a human will look at what the brain wants to do and send it. Obviously, it's not real time, like you need to send change the parameter every second. But that's actually in production now. And what's interesting is this is an illustration of actual data from the system. But you can see every time that the system goes out of the specification range, the brain can bring it back in, back in, back in, and so forth, for three key output variables. The system was so successful that even Pepsi CEOs mentioned and thanked Microsoft for this project on his LinkedIn a year ago. So for this project and many others that we have the chance to work on, we're able to extract a few key elements that are extremely important when it comes to autonomous systems projects. So let me share those with you and open then the floor for questions. First, it's a structured development process. They are those 5 steps are here for a reason. As you can see, it's very critical to be very structured, machine teaching, and so on and so forth. The second thing is deep collaboration is going to be required. Whoever is going to work on the Project Bonsai, it's very important for those people to work together to extract this information. That means that you're going to have to incorporate the subject matter expertise of your R&D team, product R&D, process R&D, the production supervisors, the operators, especially the experienced ones. And then you need to find a set of skills that are very complementary, because to put together such a system, you're going to need some traditional ML/AI, in particular if you want to do an AI simulator. Deep reinforcement learning training, of course. You need the ability to become versed into your process. So the engineers are going to build a system needs to go and work with the AI agent, the AI expert to build that. One thing I didn't mention is the data collection. I mentioned about, hey, we need to get a lot of data for that. We need to carry the data. Well, that's very nice and good, but how do we physically do that? You have to build the right database, the cloud infrastructure, whatever you need to do that if it's not existing already. You have to develop the simulation, and there are different types of simulations. So where do you get this knowledge? And then you need some intelligent edge capabilities, IoT capabilities to deploy that. But if you get everything together, you can normally get to a successful project. What's interesting also is through the steps, you'll be able to have different gates, if you wish, where you'll be able to see whether your project is feasible or not. First one, as machine teaching. If you cannot boil down the issues and things like that, the heuristics, what are the key variables, make those trade-offs, you can't go further. If you can't build a simulator that is accurate enough, you can't train deep reinforcement learning. So you'll need to be able to get through those gated factors to be able to go and develop a project.